All right, Matt 2, here we go. We got 9-7, factoring special cases. So a few weeks ago, maybe like a week ago or so, we did multiplying special cases. Well, now we're going to undo all that multiplication and factor using the special cases. Our question for today is, why does the binomial x squared plus 25 not factor using the difference of squares method? All right, so a lot of people think this should be like x plus 5, x minus 5, or even x plus 5 squared. It's not, it's prime. But anyways, so why doesn't it use the difference of squares method? All right, so this is our big method. We're going to do another method in a second, but this is the one you have to know. So this is called the difference of two squares, and the name says it all. Difference. That means that we're going to be subtracting. That's what difference means. So that means subtraction. So what's it the difference of? Of two squares. So we're going to have two things that are squares. So that means something to the second power. So something like x to the second power. That's what squares means. So I need two things that are subtracted and are both perfect squares. So that'd be something like this, a squared minus b squared. The pattern for this is that anytime that you have a squared minus b squared is the perfect square of a, b squared is the perfect square of b. So what you would do is a plus b, a minus b. That's the pattern. So if this is a perfect square and this is a perfect square and they're the difference, meaning there's subtraction going on, then we can split it up into a plus b, a times minus b, or times a minus b. All right, so this first one, is this a perfect square? Yes, that's the perfect square of x. Is this a perfect square? Yes, it's a perfect square of 7. So is this the difference of two squares? Yes, we've got a negative sign in the middle. So we have the difference, negative, of two squares. This is a square of x, this is a square of 7. So our pattern says that we can do a plus b, a minus b. So this one would be x plus 7, x minus 7. And there we go, we factored it using the difference of two squares. Next one, is this a perfect square? Actually, yes it is. This is 2x times 2x. Is this a perfect square? Yep, that's a perfect square of 9. Is it the difference? Yes, we have a negative sign. So we can say that this one would be 2x plus 9 and 2x minus 9. If you don't believe me that it works, just think back to that lesson that we did. I think it was like 9-4. Yeah, I think it was 9-4, where we did multiplying special cases. We saw that when we multiplied this, those middle two terms in the peanut, they canceled out. So that's why it's working. All right, next one. Difference, yeah, we've got a negative sign. Okay, so is this a perfect square? Well, this is the perfect square of 4, because that's 4 times 4. This is x squared times x squared, and this is y to the third times y to the third. So yes, that is a perfect square. It's the perfect square of 4, x squared, y to the third. Is this a perfect square? 121. Yes, that's the perfect square of 11. Is this a perfect square? Sure, that's z to the 5th times z to the 5th. So we have the difference of two squares. So we would say this would be 4x squared y to the third plus 11z to the 5th times 4x squared y to the third minus 11z to the 5th. All right, moving on. Why is this easy problem there? Because it's not easy. It looks like this is the perfect square of x, and this is the perfect square of 3, so what's the problem? It's not the difference. This is the sum of perfect squares of two squares, and we're looking for the difference. Do you see a negative sign there? I don't, so it doesn't work. This one would be prime. It does not factor. It has to be the difference. You have to have one positive and one negative. All right, moving on. What about this one? Okay, well, this one, I'm going to show you two different ways to do it. First of all, we should factor out GCFs when we see them. I know I haven't been telling you to look for them, but you really should be. Let's see what happens if I don't factor out a GCF here. This is the perfect square of 2, and this is the perfect square of 6x. So this would be 2 plus 6x and 2 minus 6x. Now, the problem with this is that there's a GCF inside of this one, and there's a GCF inside of that one. So usually when we factor, we're not allowed to stop factoring until everything has been factored. And on this particular problem, everything hasn't been factored. I can factor out a 2 out of that one. So this one would be 2 times 1 plus 6x, or 3x, not 6. And then I could factor out a 2 out of this one. So that'd be 2 times 1 minus 3x. Dang it, I keep messing up. All right, and then 2 times 2, what's that? That's 4. So I get 1 plus 3x, 1 minus 3x. So that's probably not the best way to do it. You have to do a whole bunch of different factoring outs of GCFs and then multiplying those two together. What we should do on any problem is always look for the GCF first. That's the first things that you always want to do. In this case, I do see that 4 goes into both of those. So let's factor out the GCF first. We'll take out a 4. 4 divided by 4 is 1. And negative 36x squared divided by 4 is negative 9x squared. So I factored out the 4 first, and I can still see that this is the difference of two squares. This is the perfect square of 1. This is the perfect square of 3x. So this part in here factors into 1 plus 3x, 1 minus 3x. Now, this doesn't multiply to get us back to where we started, and our answers have to always multiply to get back to here. So what are we missing? We're missing this 4 that we factored out at the beginning of the problem, so we're going to leave that in there. So you see how this is a lot easier than factoring by difference of squares first and then doing GCF. Stupid. They better not do happy trails to you. Oh, okay, good. They're not going to. All right, so we get 4 times 1 plus 3x and then times 1 minus 3x. Easier to get the GCF out first. On number 6, looking at this one, is 75 a perfect square? No. Is 3x squared a perfect square? No. So we might think this is prime, but there's a GCF. So what number goes into 3 and 75? 3 does. So let's factor out a 3 first. Okay, so if I had 3/4, that'd be 75 cents, right? So that's 25. And then minus x squared. Ah, now, oh, they're really doing it. I'm going to pause. I hate when they do this. I'm making a video! Stop! Okay, so anyways, this is the perfect square of 5. This is the perfect square of x. So don't forget, we already factored out a 3. And then over here, I'm going to get 5 plus x and 5 minus x. There we go. All right, so number 7, keep in mind, we're going to look for a GCF. And yes, there is one. The GCF is 9. So that would leave me with x to the 4th minus 1. Now we have to ask ourselves, are these perfect squares? Yes, this is x squared times x squared. And this is 1 times 1. So we can factor it again. Don't forget that 9 that we factored out earlier. So this is going to be x squared plus 1 and x squared minus 1. Now I included this problem because this is kind of a strange problem where we can keep on going and showing you that you can factor multiple times during a problem. What we should always ask yourself is, am I done factoring? And the answer is no, because this is the perfect square of x, and this is the perfect square of 1, and it's negative. That's the difference of two squares, so I can factor another time. Now you might ask yourself, well, could I factor this? No, because they're both positive, and for it to be the difference of two squares, one would have to be negative. So I factored out a 9 at the beginning. I still have this x squared plus 1 in there, but then this one factors into x plus 1, x minus 1. So this one factored 3 different times. We factored out the 9, difference of 2 squares to get these ones, and then this one became the difference of these 2 squares. So this little binomial over here actually splits up into 3 or 4 different factors. So the factors are the things that are being multiplied. So 9's a factor, x squared plus 1's a factor, x plus 1's a factor, x minus 1's a factor. All right, so that method, the difference of 2 squares, you have to know it. The next one, you don't really have to know it, but it makes the problems go faster sometimes. So we talked about the factoring of perfect squares when we had a plus b squared or a minus b squared. And we did it going the other direction last week. Now we're going to go forward. So if I have something squared here, and then if the middle is 2 times those 2 things, then it's a plus b squared. Here's what I mean by that. Okay, this is the perfect square of x, and this is the perfect square of 7. Well, we have to ask ourselves, is the middle 2 times x times 7? Because this is 2ab. So is the middle 2x times 7? Yes, it is. 2 times x times 7 is 14x. So what we have here is this situation, a minus b squared. Because we got a square on the first term, a square on the last term, and the middle term is 2 times the first thing times the last thing. So 2 times x times 7. So what we can do is take the shortcut, and we can just say this is x minus 7 squared. Now maybe you're looking at that going, I don't want to have to learn those patterns. Can I do something else instead? Sure. This is a trinomial without a leading coefficient. We could have just asked ourselves what multiplies to give us 49, but adds to give us negative 14. Well, 49, remember both these have to be negative because it's multiplying and giving a positive, but adding and getting a negative. So I could do like negative 1 and negative 49, or negative 7 and negative 7. Those give me negative 14, which is why I have x minus 7 squared, because it's x minus 7 times x minus 7. So do you have to know this pattern? No, you can use trinomial factoring instead. But I think this pattern is actually a lot faster on problems like the next one. The next one, is this a perfect, well, look for GCFs first, and we don't have it, thank goodness. But let's see if this is a perfect square. Yep, that's 2x. Is this a perfect square? Yes, that's 13. Now we have to ask ourselves, is this one 2 times 2x times 13? So 2 times 2x is 4x. And 4x times 13, yep, that's 52x. So what do we get to write? We can just say, oh, I know the answer. It's 2x plus 13 squared. It's this one plus this one squared. Because the middle term is 2 times this times this. All right, last one. We always want to look for a GCF first. And in this case, we do have one. 64, 32, and 4. 4 goes into all of those, so we always want to do that first. 4 goes into 64 16 times, so I get 16x squared. 4 goes into this 9 times, so I get 9xy. And 4 goes into this one time, so I just get 1y squared, or just y squared. All right, so I found the GCF, and now we're going to see if it's one of our perfect squares. This one is 4x. This is the perfect square of y. Oh, this is supposed to be 8. I did 36 divided by 4. I don't know why. Anyways, this middle term, now we have to ask ourselves, is it 2 times 4x times y? Yep, that's 8xy. So what I can do is I can just use these two numbers right there and say this is 4 from that one out there, and then 4x plus y squared. The end. Make sure to answer this question from the beginning. Hopefully you kind of saw what the answer to this would be when we did example 4. That kind of explains why it doesn't work. Have fun. Have a good weekend. I'll see you later. Bye-bye.